Hello, my name is Brad Verhulst from Texas A&M University, and in this video, I'm going to talk to you about methods of fitting twin models using the direct symmetric matrix approach. This approach stems from a paper that I wrote with several of my colleagues who are also on faculty at the 2022 Boulder workshop, and it has really changed how we've started thinking about teaching twin modeling. So let's start. When we think about twin modeling, what we're thinking about is understanding the decomposition of phenotypic variance into genetic and environmental components. So we typically discuss phenotypic variance as a sum of independent variance components, VA, VC, and VE. And we know that from a litany of statistics classes that you've probably been forced to take over the years, that we can easily calculate variance with the standard equation, which is basically the observed value for individual I minus the mean squared, summed, and divided by the number of observations. This method, the standard method of thinking about variances, encourages us to think about variance components as squared quantities. So we could think of sigma squared P, or sigma squared phenotype, being equal to sigma squared additive genetic plus sigma squared common environmental plus sigma squared unique environment. In contrast, for twin models, what we really should be thinking about them is differences between MZ and DZ twin correlations. So if we assume that the variance of our phenotype is 1, then our phenotypic variance is 2 times the difference between MZ and DZ twins correlations plus double the DZ correlation minus the MZ correlation plus 1 minus the VA and VC components, which were specified earlier. And once we start thinking about twin correlations and differences between twin correlations and stop thinking about phenotypic variance as a squared quantity, it really starts to change how we think about modeling twin methods. And who cares? So in most cases, in reality, the estimates from the direct symmetric approach are going to be very similar to standard squared variance approaches. The problem is that the discrepancy, when it emerges between the nominal and the empirical type 1 error rate. So under the null distribution, so if, for example, your C or your A parameter is truly 0, you're not going to have the right type 1 error rate. So you're not going to be testing against the right alpha rate, which means you could be concluding that your test is not significant when in fact you just used a p-value that's substantially more extreme than you were hoping to use. So this all comes down to the type 1 error rate, which is the probability of rejecting the null hypothesis by chance alone. So if we set our alpha level at 0.05, in repeated sampling, we would expect 5% of the time that we get a parameter that's significant, just due to chance alone, without any kind of nefarious behavior or p-hacking. The significance tests for ACE models are traditionally done using likelihood ratio tests, where the difference in the -2 log likelihood is between the restricted and the full model is the parameter of interest. And under certain regularity conditions, the difference between these two components is distributed as a chi-squared distribution with the degrees of freedom equal to the number of the difference in the number of parameters estimated. The problem that arises here is that under certain regularity conditions is often not met in twin studies because the squared paths impose boundaries on the variance components and the estimates of the A, C, and E components. And we are not the first people to do this. And in fact, our solution comes probably about 15 years too late because Peter Vischer and Greg Carey were talking about this way back in 2005, 2006. And there's been several demonstrations more recently in 2012. And so where they figured out how to correct the p-values, how to correct the test statistics. And so the standard logic went that in these squared twin models, or in the standard twin models, under the null hypothesis, the variance component is 0. The chi-square test is distributed as a mixture of 50% chi-square 0 and 50% chi-squared 1. So actually, it's not all that tricky to correct it. Basically, you just double your p-value. The problem is, once you go into multivariate twin models, where you've got 3 or 4 or 5 variables in a Cholesky, what happens is your mixtures become uncertain, and it can be a mixture of 5 or 6 different components of variance, and those components of variance cannot be easily calculated. So our goal here is to present a method that you don't need to correct your p-values. The p-values and your type 1 error rates are just set exogenously. So let's think about what we're asking here. So in a classical twin design, the standard specification, at least, we've got your A path here. So to calculate the twin one's variance, we'd go A times 1 times A, following simple path tracing rules, plus C times 1 times C, plus E times 1 times E. And that's going to give us an A squared plus C squared plus E squared. And that's what's going to fall into this trap of violating the regularity conditions. What we're proposing is actually really similar to this, but instead of estimating the A, C, and E components of variance on the paths, we're going to directly estimate the variance components themselves. So instead of saying A squared, we're going to say VA. Instead of saying C squared, we're going to say VC. So in a sense, it's 1 times VA times 1, or 1 times VC times 1, or 1 times VE times 1, which gets us to theoretically the same spot as we were before, but we can avoid squaring these parameters and therefore imposing an implicit boundary on them. And then we can simply state that the correlation between twin 1 and twin 2 for MZ twins is equal to VA, which is exactly what the Holtzinger or equation says it should be, also called the Faulkner equations. And VC is the correlation here. And so we can say that the correlation between twin 1 and twin 2 for MZ twins is VA plus VC, and the correlation for DZ twins is half VA plus VC, which is exactly what those methods would suggest they should be. So what's the intuition behind this? Why would this be a problem? And really, the problem comes down to we're estimating sampling distributions. So if we think about the empirical correlation of MZ twins that are simulated to have a correlation of 0.5, sometimes we're going to have a correlation that's slightly bigger than 0.5, and sometimes we're going to have a correlation that's slightly lower than 0.5, just due to chance alone. Similarly, for DZ twins, sometimes we're going to, if we're simulating them at a correlation of 0.25, sometimes we're going to get a slightly bigger correlation than 0.25, and sometimes we're going to get a slightly smaller correlation than 0.25. But if we think that we have in our true model an MZ correlation of 0.5 and a DZ correlation of 0.5, that would imply that our A parameter, our A variance, is accounting for half of our variation. So A would be 0.5, C is 0, i.e. the null hypothesis, and E is 0.5 also. And so under that situation, we're looking at C under the null, but what happens if we get slightly lucky for MZ correlation? So instead of estimating directly on 0.5, we're getting somewhere 0.52. So not a big deviation, completely within the realm of possibilities. And what happens if we get a slightly smaller correlation for a DZ twin? So instead of 0.25, we get a 0.21, right? No one's going to get too concerned that 0.21 is less than 0.25 or 0.52 is greater than 0.5. But this is really going to play havoc with our twin models. And that's going to suggest that we've got a different mode of inheritance than is really true. And it's going to violate are empirical distributions under the null. So if we estimate our variance, allow the variance components to be estimated in the direct symmetric matrix type of way, what we get is this nice normal distribution of C. Now remember, C is actually 0, but sometimes C is estimated to be negative, which may be nonsensical, but we would expect sometimes that the MZ correlations would be slightly higher or the DZ correlations would be slightly lower than we'd expect. And sometimes we're going to get lucky in the other direction. However, if we were to bound the parameters like we would implicitly by squaring them, then we no longer allow C to go negative, and instead C piles up on the 0. So anytime that MZs are slightly overestimated or DZs are slightly underestimated, that's going to end up on this 0, on the C is equal to 0, which means that we're going to bias our C parameter slightly positive, not a huge magnitude of bias, but it's going to start existing. And when we think about the distribution of the parameters, our distribution of C in this case, even though there's some nonsensical cases, is quite normal and realistic, making for easy inferences. By contrast, this distribution is a complete mess, and it's going to make it really difficult to draw any conclusions from that in terms of confidence intervals, et cetera. They did figure out prior to our paper here, especially in a really creative paper by Hao Wu and Mike Neal in 2012, that basically for a univariate twin model, so 2 variables, 1 variable per twin, the p-value that OpenMX gives can be divided by 2. So if your p-value is 0.1, you actually have a p of 0.05. For more than 2 variables, like I suggested, it gets really tricky because you're mixing multiple different chi-square distributions. But the direct symmetric matrix approach works in those cases too. So you can avoid any kind of complex math. The question that you're probably asking yourself now is, how bad is the problem? If most of the time you're going to get similar estimates, why do we care? Well, our p-values are wrong. So, if we use p-values or confidence intervals even, we're going to get it really wrong. But to dig into this, we conducted 2 simulation studies to examine the impact of these implicit boundaries on the type 1 error rate and the parameter bias that we observed. In the first study, we simulated a basic multivariate twin model where C was equal to 0, and we varied it from 1 to 4 phenotypes. And if you're interested, you can read the paper. In this presentation, we're going to focus on the 1 and the 4 phenotype comparisons. And then we took this basic multivariate twin model and fit a Cholesky decomposition, or a correlated factors model, or a direct symmetric matrix model. So both the Cholesky decomposition and the correlated factors model are completely out there in the literature, and they're really quite common ways of thinking about of analyzing twin data. And so these are the natural comparisons. In the second study, we simulated a common pathway model and then fit it using Cholesky decompositions, correlated factors model, the direct symmetric matrix model, and then the independent and common pathway models. So one of the things that became immediately apparent is that as we increase the number of variables in our twin model, the numerical and the theoretical type 1 error rates diverged. So on the top of the table here, we have 0.1, the number of times, or the proportion of times that the p-value exceeded the 0.1, 0.05, and 0.01. So we'd expect, if we're doing what we're expecting to do, that the p-value that we're observing here and the observed proportion of false positives here would be roughly the same. And so you can see that when we estimate the variance here, we do get really comparable values to our specified type 1 error rate. When we estimate the standard deviation, however, we're getting about half of that, which is consistent with what Greg Carey, Peter Vischer, and Hao Wu have demonstrated in the past, that it's really a mixture of multiple chi-square distributions. But the direct symmetric matrix approach, you don't have to do those complex post hoc calculations. Now, when we go into a 4-variable situation, again, our nominal type 1 error rate and our observed empirical type 1 error rates are really quite consistent. Whereas for the 4-variable Cholesky decomposition, you're at about almost 1/10 of the empirical distribution. And that is a substantially more conservative p-value than you're hoping to test for. So basically what this is saying is that if you observe a p-value of 0.1, if your threshold is 0.1, you're going, only 1% of the time is it actually going to exceed that. And that's a substantially more conservative estimate of your effect than you really want. So when we push this forward to do more of a hypothesis-driven type model, like the IPM or the CPM models, again, the direct symmetric, when we're using the direct symmetric matrix approach as our saturated model, when we're comparing it to the independent pathway, the common pathway models, again, we see the empirical and the observed p-values or type 1 error rates being extremely consistent. And again, when we use the Cholesky or the correlated factors, we're seeing massive deviations from our empirical estimates of the nominal type 1 error rates. And so I also mentioned that by bounding these parameters at 0, we would bias the parameters. So when we think about the Cholesky decomposition of the correlated factors model, our simulated effect of C equals 0 is in this blue dashed line here and here. But with the Cholesky decomposition in the correlated factors model, the observed value is higher than 0, whereas the direct symmetrics, we don't have any parameter bias here. But we know that the A and the C parameters in a twin model are interrelated and interdependent. And so the higher that you estimate A, for example, the less you're going to estimate C, and vice versa. So although we're showing that your C parameter is slightly biased, it's also going to mean that you're underestimating your A parameter. So you're going to unduly increase the likelihood of observing C if C is really null. And this isn't a big bias, but it's present. And you're going to underestimate A in the same model, which is both problematic from the common environment and the additive genetic perspectives. And importantly, the direct symmetric matrix approach will always fit the data as well or better than the Cholesky or the correlated factors models. So as you can see here, we've got the relationships, and we've got the Cholesky versus the direct symmetric matrix approach, the correlated factors versus the direct symmetric matrix approach, and then we're comparing the correlated factors and the Cholesky. And we can see that always the best estimate here is the direct symmetric matrix approach. And you see all of these dots that fall above this perfect correlation line being slightly worse fits because the C parameter hit the boundary. And you can see that there's several model failures in here. This big difference here really looks a lot more like model failures, meaning that the direct symmetric matrix approach is actually more likely to come to a valid solution without any problems than the correlated factors model. And this can take weeks of resolving it if you're trying to fix why did my model fail kind of problems. And it can just be empirical under identification in many cases. Okay, so we've pushed for this direct symmetric matrix approach this week in the workshop, but there are some things that we should be aware of. And to some extent, all models come caveat emptor, buyer beware. So The unbounded variance components, like we're pushing for here, may take on negative, which may seem like nonsensical values. In some cases, these values are just reflecting measurement noise, right? Sometimes you get a little bit lucky with your MZ correlation or unlucky with your DZ correlation, and all of a sudden it looks like you've got an ADE model when really D and C are both null. But as you start to diverge and get more and more negative heritability or common environment estimates, and as these estimates become statistically significant, it's possible that these values, these seemingly nonsensical values, will suggest some sort of model misspecification. For example, you may have fit an ACE model when you could have fit and should have fit a DE model. And by looking at the negative C parameter, if it's significant, it can suggest that to you. Another limitation of the direct symmetric matrix approach is that it can be tricky to fit gene environment interaction twin models. And they can be really tricky to specify within the DSM approach. Not impossible, but definitely more difficult than in a Cholesky approach. So in conclusion, when we apply implicit or explicit boundaries that we can often lead to a deviation from the type 1 error rate. And this can induce parameter bias in the estimates under the null hypothesis. When C is really 0, you can, at the extreme, estimate a positive C if you bound the parameters to be positive. And the fact that the type 1 error rate is underestimated, so is overly conservative, implies that we're missing a lot of real results. A lot of type 2 errors are being committed, and that's going to mean that we're missing a lot of that kind of information. Thank you very much. I'd be more than happy to take your questions during the workshop session. So I look forward to meeting you there.